this is Miss Litton, and I am recording this for those students who want a review of chi-square, and specifically I'll be addressing the issues related to the behavior lab. So just as a preface, and my students know about this, is understanding when data is significant or not significant. Does this data support your hypothesis or not? And how do you know to do that? So we talk about independent and dependent variables, right? Independent variables are what you're changing in your experiment, whereas your dependent variable is your what? That you record. Your data that you record, okay? So we needed to review independent and dependent. Next, I want to review with you the two types of hypotheses there are. The hypothesis that you're most used to doing is a research hypothesis, or what's called H1. And it is saying what you do to the independent variable will in fact affect the dependent variable, that they are connected. And this type of hypothesis is an if, then what? Because. An if, then because. If I do this, then this will happen because. A null hypothesis is saying there is no connection between your independent variable and your dependent variable. No connection. And there are reasons why you would do one or the other in your experiment. It could be the exact same experiment, it's just two sides of the coin. If you look here, when we did that same function machine we did before, independent variable, dependent variable, and H1 says there is a connection. If I do this right here, then this will happen. That's the dependent variable. But a null hypothesis says there is absolutely no connection. If we did this in class, for some of the classes discussed this, some did not, and we said, is there a connection between the amount of sleep you get and your grades? And if we wrote a research hypothesis, we'd say if you got 7 hours of sleep, then you would get good grades because your brain was not overworked, it was well rested. If, then, because. Now, we had this discussion in class. Is sleep the only variable that impacts your grades? What are other things that impact your grades? How much you study. How familiar you are with the material. Is there any stress in your outer stressors in your life? Do you have time to review? Do you get along well with the teacher? All those kind of things can impact your grades. So that type of experiment, what would be better is to write a null hypothesis and say there is no connection. Now, if it comes up that the data you have is overwhelming, it looks like there's a connection, then you can disprove this null. If you disprove the null, then you actually support the idea that there is a connection between the amount of sleep you have and the grades. It's just you're not saying it's the only connection. You're just implying that it is one factor of the connection. Check with your bio buddy right now that you're sitting next to and see, do you feel good with that so far? Just ask somebody. Yes. All right, and some classes got that, and some classes didn't get that far. Okay, so a null hypothesis says any fluctuations are due to chance. So if it doesn't fall exactly even, that it is chance. For instance, if I dealt out 10 cards from a regular card deck, how many would you expect to be red? Which would be how many if it was 10 cards? 5 would be red and 5 would be black. Okay? Stick with me because if you're engaged in it, that will help you quite a bit in what I'm doing. Okay? So 10 cards, I shuffle a deck. You assume I shuffle the deck. I deal out 5 cards and 5 cards over here, a total of 10 cards. I would expect 5 to be red and 5 to be black. If I got 6 red and 4 black, could that have been just a chance? Yes. Yes. But if I got 9 red and 1 black, do you think that's due to chance? Probably not. I probably didn't do what? I probably didn't shuffle the deck. So what we need to do is more than a feeling, okay? We don't just go, I think that's good data, I think that's bad data. We want to statistically analyze our data to see whether we support our hypotheses or not. So is it due to chance or not? So I want to work through a chi-square problem with you with 20 cards. And, hi, Not till 3:10.
No, I know. I'm going to find it 3:15. I'm just giving you a heads up now.
Okay, thank you.
Yeah.
Okay, so if I was going to deal out 20 cards, how many would you expect? Oh, here, a research hypothesis. I'm just going to skip this really quick. I would expect 20, if I dealt out 20 cards, I would expect 10 to be red and 10 to be black. Because in a deck of cards, 50% of the cards are red and 50% of the cards are black. That probably would be a really good hypothesis for dealing out something that you can easily quantify, right? Getting enough sleep for grades, that's a little bit harder to quantify. But decks of cards, a research hypothesis is pretty good. If I did a null hypothesis, if I said if I deal out 20 cards, I could have random amounts of red and black. That's a place where a null hypothesis isn't any good. Well, let's look at the data. 8 were red and 12 were black. Do you think that is significant? Could that have happened due to chance?
Yeah.
Or could I have failed to shuffle the cards? Okay, now let's see and let's use the math. I agree with you, but we need to say at what point is it chance and what point is there some other factor. So, if I were doing a research hypothesis and I said I was going to deal out 20 cards, in my research hypothesis, how many would you expect to be black and red? 10 each, yes? So my expected data would be 10 red cards and 10 black cards. Do you agree with that? Okay, so now I just need to see how far am I off with what I got in my results, where I got 8 red cards and 12 black. So I need to take the difference between what I expected and what I observed. So 8 minus 10 is how many?
-2.
-2. And 12 minus 10 is 2. Now I have to tell you, because you only had 2 options, if it wasn't red, it would have to be black. But if there were 3 options, you could have red, black, and pink, right? Then you could get some different numbers. But now it's just either or, yes? Okay. So then all I have to do to analyze the results is do a little bit of math. You take the difference between what I observed and what I expected and you square it. What is -2 squared? 4. Okay? And +2 squared is also 4. And all you have to do then after you square it is put it over what you expected. How many red cards did I expect? I subtracted it. I expected how many? 10. So 4 over 10. And how many black cards did I expect? 10. Okay? So you don't leave it as fractions. You have to do the math. So what is 4 divided by 10? 0.4. So 0.4, and this one is 0.4. Then you just add those 2 numbers up. What are the 2 numbers you now have? 0.8. Okay? That right there, that is referred to as your chi-squared value equals 0.8. Once you have that, you're golden. You just look it up on a chart and see if that's statistically significant or not. So let me show you here. Okay? We took observed minus expected. We squared it over what we expected. Do you agree? And then we did it for the red. Observed minus expected, squared it over what we expected. And here, okay, that number is 0.8, and then all we have to do is look up that number on a chart to see if that's statistically significant or not. Were we off so much? Now keep in mind, if I had, we expected 10 and 10, right? But what if I had 18 and 2? Do you think that's statistically significant? Yes? So 10 minus 18, because I expected 10 and I got 18. 10 minus 18 would be what? -8. And I would have to square that. What is 8 times 8? 64. Do you see how that number is so much bigger? And if I have a number that's so much bigger, when I divided that by 10, it would be 6.4, right? So the more I'm off from what I expected, the bigger my chi-square value is, right? Because I'm taking how much I'm off, squaring it, and putting it over what I expected. 0.8 is not a very big number, is it? So I probably was not off that much. So let's go look at this table, okay? This table is scary, but let me explain it to you, okay? So the first thing we have over here is degrees of freedom. Your degrees of freedom is always one less how many choices, and this is why. If it were not red, what would it be? Black, 1 degree of freedom. But if I had red, black, and pink, right? If it's not red, it could either be what? Black or pink, so I would have 2 degrees of freedom. If I was looking at like all the different suits, there are clubs, diamonds, spades, and hearts, right? On cards, if you don't know that, clubs, diamonds, spades, and hearts. So if it was not spades, then it could be clubs, hearts, or diamonds. So my degrees of freedom are 3. See how that works? So for us, the degree of freedom that we're going to be looking at, if not red, it was black. So it's just 1 degree of freedom. That's why you just take 1 away from how many choices you have. So I just pay attention to this line. Then I just have to go across this line right here. I'm just looking for that number. What number are we looking for? Point what? What did we calculate as our chi-squared value? 0.8. Do you see how it's somewhere between 0.46 and 1.07? Okay? Then that's a high probability. How high of a probability? Between 30 and 50% of the time, I would have come up with that. If I got a bigger number, like my chi-squared value was 5, then I would be way over here if my chi-square value was 5, and then it would only be between 1 and 5% of the time would I ever get that due to chance. So do you think that would have happened? No. Okay? Remember, you're looking to see how much are you off. Are you off by a lot? Okay? If you're off by a lot, you're going to have a really big chi-square number. So in this case, for our purposes, we were not off that much. 0.8 falls right where the yellow star is. It would have happened 30 to 50% of the time. I can accept those results. There's nothing wrong with my deck of cards. Okay? Let me give you another example here in just 1 minute. This is the equation for the chi-squared data. So this is chi-squared. This right here means sum of. And what you did is observed minus expected. Right? We expected 10 and we observed 12 cards. So we did 12 minus 10 and we squared that and we put it over what we expected 10. Do you agree with that? And we did the same thing for the other set of cards. And then this just means add those two numbers up. We added 0.4 plus 0.4 and we got our chi-squared value that was equal to 0.8. And then all we had to then do is look on that chart to see if it was significant or not. When it becomes significant is always in the same place on the chart, right here. It's always there. So if you only have 1 degree of freedom, if your chi-squared value that you calculate is 3.84 or even bigger, which means you are off by a lot, then your data is significantly off. If it's a small number, your data was as expected. Okay, now turn to the person next to you and say, right now, are there issues that you're thinking in your head? Go ahead, ask them. You have issues?
Yeah. Hit me up. How's that doing?
Good.
Okay, I believe you. Long day. Okay, now you will know if you really know it, and we'll apply it to your lab if we can handle this question right here. Okay, so let's try this one, because if you can do this, then you can handle anything I hand you on your test. Okay, so this says, and let's try this with, we'll do a null hypothesis. Okay, the last one we did was a research. We said, if I deal out, then I will get 10 of each because half the decks in the cards are red and black. Now we're going to write a null. here's the data we have. Currently, 35.2% of chemists, people who are chemists, they say that's, I would say I'm a teacher, but people who said they were chemists, 35.2% of them are women. Okay? So a null hypothesis would say that women are not underrepresented in the field of chemistry. That would be your null hypothesis. So now we need to set it up. How would we do a chi-square test on this? Yes?
You go straight to the table and find out the value of the value.
This is just a data point. Now, only one data point is shown to you right here. What the data point is they've given you is number of women. And what is the number of women that they say here? 30 what? 5.2. What other data could you infer from that?
64.8.
Yeah, so we could infer the number of men because we're assuming they equal 100%. Right? Have you got that? So what's 100% minus 35? Use your calculator, you're going to need your calculator. Use your phone, I don't care, use a calculator. Right? So I have 64.8 then would be male. But if they are not underrepresented, then you would have 50% of them be female and 50% of all chemists be male, right? So when we look at it this way, if 50% were female and 50% were male, observed 35% were, but I would expect 50. I take the difference, 35.2 minus, I expected 50%, that's a difference of 14.8. Look up here just for a minute. What would I have to do to that 14.8 number? Square it. Now I get 219, which I have to put over what I expected. What did I expect? 50. So what is my what is this one right here? 4.4. Now let's do it for the male. Same thing. 64.8 minus 50. It's overrepresented by 14.8, right? Squared. It's still 219. Still over 50 because I'm very binary in this one. I'm saying if you're not male, you are female, and vice versa. So 219 divided by 50 is also 4.4. Remember, the equation is the sum of the observed minus expected squared over expected. So I need to sum those two up. What is the answer then? 8.8. Okay, that is my chi-squared value. Once I've summed it and I have my chi-square value, then I can go look at a table. And let me just get rid of this real quick. Okay, so this is just a smaller table. I just wanted to expose you to the big table so it would never intimidate you. How many degrees of freedom do we have? Well, we had how many choices? We had 2 choices. If you weren't female, you were male. Take away 1, and you're left with 1 degree of freedom. I go across here. What's the number I'm looking for? See how they're smaller and they're getting what? Bigger, bigger. As I work my way around here, bigger, bigger, bigger. Have I hit 8.8 yet? No. Have I hit it yet? No. Less than 1% of the time would that come up due to chance. And if it would happen 5% of the time or less, we got to throw it out. Something is up. So our null hypothesis said it's not women aren't underrepresented in the field of chemistry. However, if so, the data we have shows that that null hypothesis is a very poor fit. Okay, less than 1% of the time that would happen. So our null hypothesis is not accurate. So what's the other side of the coin? What did we just end up supporting? That women what? Are underrepresented in the field of chemistry. Do you see that? By disproving the null, I'm supporting the research. If I write a null hypothesis, sleep does not impact your grades. But then I get a bunch of data, and a lot of things impact your grades, but what comes out is that the grades are significantly better for those who did get sleep. So now I disprove my null, and I support that sleep is a factor. Okay, so now let's apply this to our roly-poly chambers. Okay, in our roly-poly chambers, friends, this is not looking good. Okay. I don't know if it's going to get any better. Okay. In our roly-poly chambers, this is really not bad. Just bear with me. Okay. In our roly-poly chambers, we put, okay. In our roly-poly chambers, we put, let's say, how many? 8? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. I'm trying to get them to be separate. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If we put 8 on both sides, and if we covered this one with a shade, we made it darker. Okay? And I had you write null hypotheses. And your null hypotheses said light and dark doesn't have any impact, right, on roly-poly behavior. If, however, though, you end up, if, however, you end up getting, oh, look, 2 came. Okay, let's put one more over there. If after 10 minutes, this was your results, right? How many did we put on each side? 8 and 8, right? So if we put on here, we have observed, we have expected, and we have dark, and we have light. Okay? We expected if we started with 8 and 8, we should have what? 8 and 8 at the end. If it's a null hypothesis, remember null means no connection between what we're doing and what our results are. Yes?
What if your null hypothesis is proved? Like in my case?
I'm going to talk to you about that. Just give me a second on that one. Okay? So if our expected, we started with 8, we would expect to end with 8 on each side. But in this case, what was our data? We only have 3 over here, so what does that mean we have on the other side? 13. Okay? So if that's what you got, you take observed minus, and let me just move this away a little bit. No. Don't get that. Okay, good. Okay, there we go. Go up there. Okay. All right, you go right here. Okay, so now what do we do to evaluate this?
You subtract the...
Okay, so observed minus expected. What is this number right here? 13 minus 8. 5. And then 3 minus 5 is negative 5. Then what do we do to those? Square them. Okay, so what is 5 times 5? 25 over, what did we expect? 8. And this would be 25 over 8. So find out what 25 divided by 8 is. Okay, I got 3.125. Is that what you got? Okay, so this would be 3.12 plus 3.12. What is 3 plus 3? That would be 6 point what?
2.
That is our chi-squared value. Our we would say our chi-squared is 6.24. Now we need to go, is it significant? Does it sound like it's significant from what I've shown you already?
Yeah.
Yeah, let's go back here on our chart. Okay? And let's find our number. 6.64, and our number was 6.24. So between 3.85, so that data was off. That data was off. Well, off for a null hypothesis. A null hypothesis says there's no connection between light and dark. Okay? Our data doesn't support it at all because we're off by too much. So if our null hypothesis said there is no connection, the alternative hypothesis, the research hypothesis, says there is a connection. Do you see that? So by disproving the null, we can statistically say that there was a connection between the amount of light we got, how much light they had, and where they went. So what you'll do in your lab book, if you'll see, I told you in your lab map that you have your data table, right? And I said underneath your data table is where I wanted your calculations, yes? So you would do your chi calculations for your light and dark, and your chi calculations showing me all your steps for your whatever you use, Cheeto, no Cheeto, salt, no salt, whatever it was. And then you would tell me if that data was significant or not. Okay? Yes?
So I have a couple questions. So first off, on the, like with the woman in the workfield of chemistry, so since it gave us a percent, how are we to decide like how many, since if there's more, if there's a bigger amount with the same proportion, it would be even less related, like it would even further disprove the null hypothesis. So if you had like less, it further proves it,
Oh, I'm not 100% sure what you're saying, but let me try. Okay? The more if you write a null, let me just say it, okay? If you write a null hypothesis, you're saying there's no connection, right? Okay? It's saying if I punch her in the arm, there's no increase in pain. That's a null hypothesis, right? Okay? That's a null, there's no connection. So, if we in fact can measure how much her tissue has been, hurt and her response by her face, we can say, oh, there was pain. Now, if I go like this, there's not a lot. Okay, then there's gonna be, okay? So I would be off by a lot, yes? If I'm off by a lot from what I expected, it's going to disprove a null. On a research hypothesis, if you really think it is a good research hypothesis, do you want to be off by a lot?
No.
No, you want to be off by just a little.
But my question was, since you only gave us like percentages, if we took like the actual amount of like women in the workflow, it would be like way higher. Which
oh yeah, I didn't use numbers. I used percentages.
So you would give us numbers, right? Since
yeah, I could tell you I had this many baboons. I did this, I did that. What would you expect? Yeah.
Yeah.
And so then you would we just use percentages because I gave it to you in percentages, so your expected was in percentages. If I give you numbers, if I say to you there were a total of 24 apples that I randomly got from the grocery store, and you said there were red apples, green apples, and pink ladies, right? You would expect 8 of each, right? So then you would put expectation as 8. Okay, and then you would look at the data, and if I gave you mostly red apples and only a couple pink ladies and a couple green apples, then you would write how many you got and then look at the difference and do all your work. If I give it to you in percentages, keep it in percentages. If I give it to you in actual numbers, keep it in numbers like your roly-poly lab.
And then also, technically, wouldn't there still be like, there's still like a slight chance, right? That it
but this right here is what's acceptable.
Okay.
I'm going to tell you, if you worked for a big pharma company, a pharmaceutical company, they can't handle 5%. Okay? Because they don't want to go, well, 5% of the people who take our drug die, but we're going to go ahead and market it anyway. Okay? Would that be acceptable? No. So 1% isn't really acceptable. They want it, what they consider a poor fit, right, is going to be super because they don't want people to die.
And the more they test it,
yeah,
closer.
Yeah. Well, not always the more. It could be the drug.
Yeah.
It could be the problem. Yeah. So you need to change your drug. Okay, wait. I need to go back. You were the first question, and you said, "What if my data doesn't say they preferred light or dark?" So your data if you do the chi-square test, I think it's going to show that light and dark didn't have any problem. But in your analysis, claim, evidence, reason, your reason is, I think our roly-polies didn't move unless we poked them. So I think our roly-polies were dying, so they could not move as well. So in then the error, you would write, we got really bad roly-polies. Somebody poisoned them in the last class, so when they got to us, only when they were in significant distress would they ever move when I poked them. You see what I'm saying? Your data is as your data, but you have a reason why you think your data was bad, and that could account for the error, because if all of us had been given fresh roly-polies just from the soil, probably would have given us better data. So your data is, but we can understand why. Right? Okay, what else? Yes?
For the different square root of the expected, why would it be 13.2, or sorry, 3.12, not 3.
Where are you at? You need to tell me which thing you're referring to.
Sorry, for the roly-poly experiment, when you were finding the...
This one.
Yeah, why was it 3.12 and not 3.13? Because it was 3.125.
I just didn't read it. I just stopped. Yeah, you're fine. Yeah, this would have been 3.2 or 6.26. It still would have, been significant. Yes?
So for like your reasoning, you explain your chi-square value and how it's significant or not, and like the percentage that...
Well, if you go back to claim, evidence, reason, you would say, you would make a claim, depending on your data, light does impact roly-poly behavior. My evidence is when I perform the chi-square test on my results from my data table, my chi-squared value was which is a significant deviation from it having no impact. Do you see that?
Oh, that's a lot smarter.
Right? And then you would give your reason, because roly-polies are generally found under the rocks, which is dark, and the error would be these roly-polies probably weren't fresh. You know, some of them had been sitting here 5 days. Some of them were brand new. You know, some of them your mom dropped off mid through the day. I appreciated that, which is I'm super thankful for. Otherwise, we wouldn't have enough sixth period. So roly-polies got dropped off. So those roly-polies were super fresh because that came from a dog walk, not from the poo, but from walking around. Yes.
Would he do claim evidence reasoning for like both experiments?
Yes. But I don't have a problem with, you would combine it. I would say roly-polies prefer the dark and pita chips, you know, and then you would give your evidence for those two statements. And then your reason, and then you can combine that easily into one claim, evidence, reason. Yes?
Could an error be the different sizes of the roly-polies? Like they might have been
because we had mammoth ones and baby ones.
Okay, because that's like really
Ideally, I would have exactly the same, and some of you had 9 roly-polies, some of you had 8, some of you had 7, right? So we have the larger the sample size, probably the more reflective, if that's going to be of accurate data, right? If we only had 2 roly-polies and we did this, you know, you'd expect, well, I expected 1 and 1, but instead I got 2 and 0. You know, 2 minus 1 is 1. 1 squared is 1 over what I expected, 1. 1 plus 1 is 2. Okay? So that's not enough information for us to go off of, right? Okay, what else? Yes?
Do we have to do this for every minute?
No, just you're at the 10 minute.
Oh, so just the end.
Yeah.
Yeah.
At the end of 10 minutes, I'm assuming at the end of 10 minutes, they have reached their final, they've had 10 minutes to reach homeostasis in that chamber, and after 10 minutes, that's when you do your chi-square. Yes?
So would our evidence be that our hypothesis is that there wasn't a connection, and then the chi-square disproved that, so then it supports...
Your evidence is that you were off, right? It was statistically significant. So your null hypothesis, which you based your chi-square on, right? Because if you wrote a research hypothesis, you might have said 8 and 8, and I expected 16 and 0. Right? If you wrote a research hypothesis, if they actually liked the dark, you would expect 16 over there and 0 on the other. You're not doing a null hypothesis, you're not doing a research hypothesis chi-square, you're doing a null hypothesis where you expected 8 and 8, right? So you're going to say I was off. You know, it was statistically significant how much I was off. So that does not support my null hypothesis that it had no impact. It supports my research hypothesis, which would, you know, be that it did have an impact. Yes? Yeah.
For the graph, when plotting different points on the same graph, do you connect the
Yes.
5 points?
Yeah, connect it in a smooth line, all your dots, smooth line, not best made line, but a smooth line, and then label that like dark, and then do your Cheeto one or your whatever one and label that one.
So
You don't plot dark and light because then it would just go like this, right?
Yeah, you plot your control.
No.
No, your other one.
Right,
that's
you're
not
independent.
The control.
Yes. Okay, got it. Any other questions on, do you feel like you understand it better? Yeah, and if you have, go ahead, do your one question.
Should I resume it in sentences or should it be like paragraph?
It should be claim, evidence, reason, error. And I would probably put a little, and you underline it with your colored pencil. Yeah, and incomplete sentences, yes. Okay? Do you feel like you have a good grasp on it?
Yeah.
Now, if you're here tomorrow, how many of you are going to be here tomorrow? So this is going to be a repeat for you, but you'll be able to help those around you because you'll be like, splish, splash, I got this. All right? Make good choices. I hope you have good evenings, and yeah, stay healthy.